Hello, everybody. We are talking about balanced chemical equations, and we are going to use those balanced chemical equations this time to actually do some calculations about how much the amount of stuff that you need inside of a chemical reaction. We're actually going to use these balanced chemical equations as a recipe, and a recipe for making compounds in a chemistry laboratory. Now, when you look at any sort of recipe, this is one of my favorite cookie recipes right from the bag of chocolate chips. What does it tell you? It tells you the ingredients, what should go into the product. It tells you how much of each thing, and it gives you special instructions. What do you need to do in specific circumstances? That's exactly the same sort of thing that you are going to get in a balanced chemical equation. If we look at this balanced chemical equation, this is also a recipe, and chemistry uses these equations as a shorthand. This is a wonderful shorthand for how to write a lot of information in a very small confined space. We take hydrogen gas plus oxygen gas, add a little heat to it, ignite it, and a lot of water vapor is produced. Now, we don't usually include energy in chemical reactions, but this is a very exothermic chemical reaction. Exothermic means, thermic means heat, exo means exit. So this is a reaction where a heck of a lot of heat exits, energy is produced, and when you see a rocket take off, often, if they're using hydrogen and oxygen as the fuel, these beautiful white plumes that are produced are nothing but water vapor. This reaction is so violent, the energy produced is enough to launch huge, massive machines that weigh tons and tons and tons into orbit and beyond. So this is a fabulous little recipe that tells us the ingredients, how much of each, and special conditions for that reaction. It also tells us the ratio. How many hydrogens do we need for every oxygen? For every batch of cookies, you need so many eggs and so many cups of flour. Same sort of thing in a balanced chemical equation. In our past, we've also talked about moles. Moles are how we measure amount of stuff, amount of material in chemistry. And if you recall, 1 mole is equal to Avogadro's number of particles in anything. If you're talking about atoms, if you're talking about molecules, it's equal to 6.022 times 10 to the 23rd of them. And 1 mole of them is going to have the mass, if we're talking about an element, of that element's mass on the periodic table, or if it is a molecule, it is going to be equal to the sum of the masses of all of the individual parts. So Avogadro's number and the mole, this is the key for actually doing math with chemistry. So we're going to put these two pieces together, the concept of the mole and these balanced chemical equations, and we're going to put these together to do something which is called stoichiometry. Now, stoichiometry is a big, scary sounding word, but it's really not a terribly complex concept. It's when we use relationships between the reactants and the products in a chemical reaction to determine the amount of each. How much product are you going to get? How much reactant do you need? Very much like analyzing a recipe. Now, the word stoichion is Greek that means elements. Metron means to measure. So the interpretation of the term stoichiometry basically means measuring elements. It is a scary name, but it is really easy to do using our TIE fighters. So have no fear, we'll walk you through some stoichiometry. In order to do the stoichiometry, we're going to start with a balanced chemical equation, and we're going to use that to predict the amount of products or reactants involved in any sort of chemical reaction. These are the steps we're going to follow. We're going to balance a chemical reaction. Then we're going to circle the two things we're converting between. We've used this technique in the past when we were converting between moles and mass and Avogadro's number. We're going to do the same technique, but this time we're going to circle the two things we're converting between in that balanced equation. Then we're going to put the two things we've circled in a TIE fighter, our friendly little TIE fighter over here, and use that to solve for our unknown. So let's go ahead and do one of these so you see what the hey I'm talking about. We've worked with this reaction before in other talks. Sodium solid plus chlorine gas react to yield sodium chloride solid. And I want to know how many moles of salt will be produced if you begin with I'm going to add 3.00 moles of chlorine gas. So first step, make sure you have a balanced chemical equation. We've done this in the past, so I'm going to do this kind of quick. I've got one sodium, one sodium. Those are good. 2 chlorines. How do I get 2 chlorines over here? I'm going to add a big 2, change that coefficient. That's going to throw this one off balance. I'm going to add another 2 there. Next, circle the 2 things you are converting between. So we're going to convert between salt and chlorine gas. So those are the 2 things I'm going to circle in my balanced equation, chlorine gas and sodium chloride, which is table salt. Put these into a TIE fighter and solve our equation. So we're going to start with 3 moles of chlorine gas. So we've got our 3 moles of chlorine gas. Nice straight line. Start with our TIE fighter. We are going to get rid of chlorine. So these are the 2 things we're going to use as our conversion factors. We have 1 as the coefficient in front of chlorine. We just don't typically write 1 as a coefficient. So we're going to put chlorine. This represents 1 mole of chlorine gas here for every 2 moles of sodium chloride. That's the ratio in this recipe. I am going to use 1 mole of chlorine gas for every 2 moles of sodium chloride that's produced. That's like saying for every 2 cakes that I make, I need 1 pound of butter. Boy, that sounds like a good cake. Anyhow, now, before I do any math, I have to double check that I cancel the units that I want to get rid of. Moles of chlorine are going to cancel moles of chlorine. I'm going to end up with moles of sodium chloride. Do the math. 2 times 3, 6 moles of sodium chloride. Exactly the same process that we've used in the past to convert feet to inches, moles to grams. Let's do another one. How many moles of ammonia will be produced if 7.21 moles of nitrogen gas are reacted? Start with our balanced equation. To balance this, I've got 2 nitrogens. I'm going to put a 2 here to give me 2 nitrogen. 2 times 3 is 6 hydrogen. I'm going to put a 3 here to have 6 hydrogen. I'm going to start with 7.21 moles of nitrogen gas. So 7.21 moles of N2 gas. I'm going to have my TIE fighter. And what's my goal? My goal is to get moles of ammonia. So over here, I want moles of ammonia. NH3 is ammonia gas. So the 2 things I'm converting between are nitrogen and ammonia. Use these and put these in my TIE fighter. I want to get rid of nitrogen. There's no coefficient, so that represents a 1. So 1 mole nitrogen gas and 2 here, so 2 moles of ammonia gas. Double check things cancel. Moles nitrogen, cancel moles nitrogen. I'm going to end up with moles of ammonia. 2 times 7.21 will be 14.42 moles of ammonia. Pretty simple, huh? All right, let's do another one. Hit pause, try this. As always, you gotta do it on your own. You can't just watch somebody else do something. You gotta actually do it yourself. That's how you learn. And then come back and we'll do it together. Okay, to balance this, 4 goes here, 3 goes there, and then we are good. We are converting between 2.4 moles of potassium chlorate, and we're going to end up with potassium chloride. This is my potassium chlorate, and this is my potassium chloride. So I'm going to have 2.4 moles of KClO3. Here's my pretty TIE fighter. I want potassium chloride. Which one do I put on the bottom? Well, I want to get rid of potassium chlorate. So 4 moles of KClO3. Where did the 4 come from? Came from that balanced reaction. And 1 mole of KCl. And where did the 1 come from? If there's no coefficient, there is an implied, you've got 1 of them already. That's that ratio. For every 1 potassium chloride, you have to, in this chemical reaction, have 4 potassium chlorates. This I'm going to have to pick up my calculator for. Can't do this one in my head. And when I do it, these cancel and I end up with 0.60 moles of potassium chloride. Let's try one more. Okay, hit pause, give this a go. To balance this, a 3 goes there, 2 goes there, should be a plus sign, I forgot that, and a 3 goes there. Okay, oxygen and ethanol, 6.5 moles of ethanol, C2H5OH, TIE fighter. And I'm going to end up with oxygen. So I want to get rid of ethanol, keep oxygen. For each 1 mole of ethanol, C2H5OH, I'm going to use 3 moles of O2 gas. 3 times 6.5 is going to be 19.5 moles of O2. Not bad, huh? All right, you can handle these. Now you will get practice on this week's homework assignment. What we are doing in this class, folks, is we are doing moles to moles stoichiometry. And stoichiometry can get a lot more complex. It can get more complex because you just take it further, where you convert from the moles. Once you have the moles, you can take those moles and convert them into Avogadro's number and convert them into atomic mass. And quite frankly, you have the skills and you can do that. But the course that you are currently taking with me, if you're one of my students, is a basic chemistry class. And it's pretty simple, and we're just not going that deep. If you're watching this video and you have another instructor and taking another class, just talk to your instructor and make sure that you understand how far and how much you need to know. All right, have a fabulous, fabulous day, and we'll see you later. Bye-bye.